Hay que verificar ahorita que lleguen a ver quiénes van a presentar, porque sí, en todas están faltando presentaciones. Sí. Ni que no son todas las que subieron a nuevo. Sí.
Session on food systems trade and diets in a changing world. This is a very visible area of work at the moment, and it's a very important area because it also intersects across many domains, notably the environment, justice, food, health, and others. And it's incredibly policy relevant. It's something that we need to act upon to really achieve the kind of world that we want to achieve. So we have some really excellent presenters. We have Nathan Springer sitting to my right here, Maxim Chepeliev, Donna, and Siwa and Ron Sands will actually be helping us here virtually. So each of you are going to have about 10 minutes, and then we're going to be able to have 5 minutes for questions and clarifications. The session is supposed to go from 11:30 to 1, so let's stick to the time as best as we can. And if necessary, we discuss any other points in the coffees or over a beer or as you. So, Nathan, perhaps you can start yourself, okay?
So, thank
Great.
you.
Thank you.
Thank you. Okay, let's see. We gotta go back in here. You get to see a slide I'm not going to talk about actually. So you can ask me about that one later. Exactly. Question. Yeah, if we had 20 minutes, maybe we could get there, right? But maybe not 10. So I have to go back to the beginning here. I guess I just maybe click through all these. So you guys can see everything I'm going to talk about. This will be great. All right. All right. Thank you. Thank you, Mario, for leading the session. Thank you, everybody, for joining. I'm Nat Springer. I'm a research scientist in economics and sustainability at the Institute on the Environment. And my colleague Mo Olenberg is here. She also works on this project with me, and I'm going to be talking about the Foods Cube model. We've been building this model at the University of Minnesota for about 10 years now. We've been working with this approach. I've been part of this project for about 7 years. And yeah, I just wanted to give you all a little bit of overview of what this model is, how it works, and then really get your thoughts on maybe some ideas about where we're going with it. This is a model that we've had for a while, but we've really never brought it to a community like this, where we're comparing it to other models, thinking about how we can expand it, how it aligns with other folks. So that's really the goal of this talk, and hopefully we'll have some good discussion afterwards. So again, this is our team. So Jennifer Schmidt, she's been the one leading the project since the beginning. And then we have Will, Mo, Riley, Arup, and Annabella, who are all working on this project right now with us. Let's see here. All right. So with Foods Cube, what does it do? We model supply networks in the US, and we estimate their spatially explicit environmental impacts. We're coming at this from a very explicit life cycle perspective. So the reason the model was built in the first place is we had some partners in the nonprofit world who were basically asking questions like, where does corn come from in the US, and what is its environmental footprint? And so we built this model to answer that question. And so you can see the map on the left there is modeling the movement of corn at the county level in the US. And then this is modeling the embedded impacts in that corn as it moves. So since this is a modeling conference, I thought I'd just get right into how the model works. Again, we look at, we're really taking a commodity specific approach. So we built this for corn, and then we've since expanded it to soy, wheat, alfalfa, and we're really thinking about it too from an animal footprint perspective. So a lot of the colleagues and stakeholders we work with are interested in the impact of meat for obvious reasons from an environmental perspective. And so we look at cattle, dairy, pigs, chickens, including broilers and layers. And then one of the things that we do is we map these to explicit facility scale. So we collect facility data for things like ethanol production and soy crushing and wheat middling operations in the US, as well as looking at slaughter facilities and milk processing facilities at the end. So we really get this really heterogeneous model where we're able to look at supply chains at the sub national level and really build supply sheds for these different commodities and look at their environmental impacts. Oops, going backwards. So the model itself is very simple. It's just a transport model. So basically, we're just minimizing the transport costs between regions. And how we make that work is we estimate, we get data on demand at the county level or the facility level and supply at the county level. So both supply and demand are exogenous. They're constrained in the solution. And then we use impedance factors to see how this stuff moves around. We've also played around with cost as minimizing costs in a different way. But we can talk about difficulties and estimating costs at the scale that we're doing it to make this work. So really how this works, right? So if we're running corn, whoops, pressing the wrong direction here. We run, well, the way we get this to work, since we're doing every county in the US, right, which is computationally intensive, we run corn, each stage of the supply chain separately. So we run supply for corn, so demand for corn for all these different commodities, and then we model the transport or the export, which is E. And then you can see what we do then is then we know the sub demand for these categories afterwards. And then we can estimate sub demand for these and build out individual supply chains. And so what we then do is then we take that and we run that for that same model for other things, like we'll run the cattle model to the slaughter facilities and estimate transport. And then we can model things like the demand for ethanol and the transport. So we run each stage of the supply chain separately, and then we put them all together. And then what you can do is you can estimate the life cycle emissions impacts at each one of those stages. So this is where the life cycle assessment comes in, right? We're trying to estimate from farm gate all the way to the slaughter facility what the life cycle and environmental impact is. So G would be the coefficient that you would use for that impact at each county. So we're using county level impact factors for each of these things. And then you can get these supply sheds where you can basically ask the question like, well, what for a given set of slaughter facilities in the US, what is the upstream environmental impact of the feed going into the meat that you're consuming or that you're producing? So that's the logic behind how this works. As you can see, it allows us to make really interesting supply chain maps, both at the national scale and at the subnational scale. So this is what we did for dairy feed. So we would take the emissions from different crops of dairy feed at different counties around the country, and then you can sum them all together and make a really interesting county level emissions map. And thinking about things like the top states, top counties, top facilities of emissions. So, and then, you know, for at the company scale, since we're doing facilities and we know facility ownership, we can do things like this, and we can rank actually companies' emissions by where they're sourcing their products. So you can see for dairy, we can say, well, some companies are doing a bit better just by a fact of where they're getting their, both getting sourcing the milk from their dairies, but then where those dairies are getting the feed that is going into their milk. So this is the kind of thing that companies like to see because it helps them target some of their strategy about who and where they're going to work with to try to reduce their impact and kind of a tier 3 emissions perspective. So again, these are some of the research questions we can ask, which is, you know, looking at supply sheds for different places, for different commodities, for different actors. And we do simple scenarios like what happens if you reduce the environmental impact factors for specific things like feeding cattle 3-knot to reduce their enteric fermentation. So those are the types of things we can do. I'm already running short on time. So the thing that we really are moving towards, and I'd really love to get your thoughts on, is where we're moving the model. Because again, it's a simple transport model, and we can't ask really interesting questions that I think our data is set up to answer. So we have this really detailed supply chain model, but we can't really answer a question like what would happen to beef production if there's a drought? What happens if supply changes? Or what if there are labor shortages because of COVID, right? In these particular facilities. Like we have the facility data, but we don't have a model that can actually answer that question. So where we're going with this is we're thinking about two things really. One is how do we actually think about resilience in these networks? Like how would you actually know if the supply chain is better off after an intervention or worse? So we're looking at the supply chain literature to start to think about resilience metrics, like how would you actually measure things like connectivity between the centrality, things that could actually tell you what your network looks like and whether it's stronger or worse after a given fact. And then we can test this resilience by looking at network disruptions, right? And And we can do that even right now, since we have exogenous supply and demand. We can actually just change, you know, the capacity of these facilities and see how the model adjusts. But because, and this is how you would do it. Like if you want to do a drought scenario in our model, you reduce the crop supply, you could reduce layer supply for eggs, or you could reduce slaughter facility capacity if you wanted to look at pork. But the problem is the model itself, because supply is exogenous, we don't get any of the rebound effects, right? Like we have a lot of econ modelers in here, you know how this works, right? We need to be able to have feedback effects if we're going to be able to model scenarios. So what we want to do is try to start to do this on the physical side, because we're doing physical commodities, but we want to be able to, and we want to keep our commodity specific scale of representation, right? We want to keep corn, soy, wheat as separate sectors. So what we're trying to start to do is think about, well, how can we make supply endogenous in this framework, and then simulate the random disruptions in this resilient space. So we're thinking about biophysical transport models, kind of with the shadow prices being built into the dual of the linear program. So we're just starting to get there. So I'd love your thoughts on ways that you're thinking about doing this at this scale, other folks who are trying to build models kind of like this, so that we can better ask resilience type scenarios and build resilience questions into the types of information that we can give to our stakeholders. And I think that's all I have for now. And again, other things I'd love to talk about, but we can talk about that later if folks are interested.
Super interesting. Yeah. Questions? Dominique.
Well, I have a question and a comment.
Yeah.
The question is, are you dealing with international trade?
Yes.
And the comment is that Tom Rutherford and Ed Balistreri are currently trying to estimate interest rate trade using a lot of data from the ports, for example. It might be good for the two of you to connect.
Absolutely. Yeah. So for international trade, we treat both, we do count both imports and exports as supply and demand. We do it exogenously, right? We just take the data, but we're taking it from GATS. We just take the GATS data. And then for a given port, we'll count that as either supply or demand at that county at which the port is. And the GATS has really good detailed commodity specific data. So and actually the figure I showed before, which is the international trade one, that's actually just presenting the international trade data tied to our local US specific model. Yeah.
But that's one thing in terms of resilience, right?
Right.
If there's a drought somewhere, well, you just import more from China.
Exactly. Yeah. Yeah, exactly. Even if you're not looking at production, if you're allowing those imports to increase for some reason. Absolutely. Thank you. Yes, great.
Yeah, we talk about resilience. So do you have some indexes or metrics that you measure this resilience? Yeah.
And I think that's what I was suggesting. Like we started looking at the supply chain literature to try to do this, and we have a postdoc, another postdoc I mentioned, Will Lockhart, who is working on a paper that's kind of quantifying some of the metrics out there that people are using to look at resilience and supply networks, and just trying to decide which ones are best used for the types of scenarios we're looking at. So we haven't picked any yet. We have some ideas, but we're still learning. So if folks have ideas, I would love to hear.
Yes, I just have a similar comment to Dominique, because there's another US intra-regional trade CGE model.
Okay.
And their main conclusion was that be careful when you use the commodity flow survey.
Okay.
Because it only accounts for about 20% of all the grain movements in the US.
We're not actually using the commodity flow survey. We're actually using US Census data. And so we're using both the production and the demand data, which has its gaps as well. And we're using some interesting things to most we're doing, like we're using the cropland data layer, for instance, to fill some of these gaps. But then we're modeling the trade. And I think, that's what we're using that a little bit to baseline what we're doing. But to your point, that's important because, and it's one reason we've started with a commodity specific approach, because it's like, we want to get each commodity right to a certain degree and making sure that we're accounting for all supply and demand in the movement, without having to try to tease out the top down approach, which is a little bit harder sometimes. Thank you.
Yeah, one last question
Absolutely.
from me. Will you ever include actors in,
Good
you
point.
know, agents that are in charge of moving all the products around? Because you could actually start looking at what happens with, multinational companies or the really big companies with SMEs, with the small consolidators and others.
Yeah.
You could actually really start thinking of, well, how if you take out some of the key actors, what would be the consequences of that?
That would be an interesting scenario too. You're right, because different companies behave in different ways and they have different operations in different places. And we could do, because we have ownership of facilities throughout this, we don't really have it at the livestock scale or like the transport scale, like you're saying, but it would be interesting to consider company specific scenarios because they might they might go out of business. I mean, that happened to Dean Foods in dairy, right? Like they went out of business, they consolidated, they sold all their stuff out. Like that kind of disruption is real too. So and in the behavior aspect, we haven't thought about it all. But even just saying, who are the actors in the space, right? The level of granularity we're getting to, at least on the supply chain side, we could start thinking about that. So I appreciate that comment. Yeah.
And you can start trying to compute value addition in the future.
Explain that again. So
compute value addition, you're going from raw commodities to
sure. So value added. Yep, absolutely. And that's what I mean. And I think getting to the dual of the model where a lot of these we're really looking at the physical side of it. We really haven't looked at the dual yet, but those are implicit. And I think as we start to make those explicit, you're right. The value add is there along the supply chain.
Okay. Well, great. Thank you a lot, Nathan. I think Sim will tell us a little bit about bending the curve of food loss and waste. So this is going to be quite interesting. Hopefully.
So it's the one on global transition.
The one on FLV. With FLV.
Do we?
FLW. Great, thank you.
Thank you.
Good afternoon, everyone. My name is Maxim Cheblik. I'm from Purdue University, from the Center for Global Trade Analysis, and this is a joint study with colleague from Wageningen University, Alessandro Gatto, and this is part of the Eat Lancet 2.0 dietary transition study. So in this presentation, as Mario mentioned, we'll be looking into food loss and waste and its interaction with dietary transition. So this is work in progress. The paper is currently under second round of reviews with Lancet Planetary Health within the special issue of the Lancet study. So to provide a bit of an overview where kind of things currently stand in terms of the state of the art of this literature in this area. So healthy diets, once we transition and change their consumption trends, there is an expectation that they would reduce food loss and waste, although not many estimates have been done to what extent. Obviously, the composition will also be changing. Some commodities like vegetables and nuts, they have higher food loss and waste shares versus others. So there could be some spillover effects. Obviously, once you reduce the demand for some food, there is a rebound effect in terms of also reducing prices and increasing demand. And we have a trade spillovers through international trade. So it's important also to account for these type of interactions. And there have been some studies, including the first Lancet, for instance, studies that looked into some of these aspects, but using a more simplified modeling frameworks like either partial equilibrium models or static input-output type models. So essentially what we try to do here is to develop a more comprehensive framework and then look into interaction between food loss and waste and dietary transition policies going forward till 2050, the long-term study. So what we, in terms of methodological framework, what we do here, and I'll discuss over the next couple of slides in a bit more detail. So we essentially combine a global food loss and waste database that we have developed with Alessandro last year. It's publicly available, it's published, so there is a reference here. And we combine this database with a model, global computable general equilibrium model. So it's macro model, it's global, covers the whole economy, so it traces food from farm to fork. And we account for food loss and waste across stages, across commodities, embedded in trade. We also take into account food flows, so both macronutrient, calories, and when defining food loss and waste, we follow their UN definition, so we are consistent with what Sustainable Development Goals kind of state in this regard. So briefly on the database, what we did kind of a scoping literature review, trying to improve the food loss and waste estimates early and available from the Food and Agriculture Organization. So essentially here we have different regions, different stages of food loss and waste. So we differentiate 5 stages like production, harvest, post-harvest loss, manufacturing, distribution, consumption, and different commodities. So as you can see in our database, the coverage of the available estimates of food loss and waste is much higher than what has been available in the FAO estimates before. So, and then we combine this database with a global economic model, so computable general equilibrium model, and with which we group the data that we have into 36 sectors, 14 countries / regions, keeping agricultural and food details as to the extent that we can. We also have environmental accounting, so we have greenhouse gas emissions, we have air pollutants, we obviously have food loss and waste flows. And essentially, this is an economy-wide framework, right? So it covers all sectors of economy. So we have a trade-off here. It's on the ag and food side is somewhat less details than some of the partial equilibrium models, but it does account, for instance, out-of-home food consumption. It does account all other sectors like transportation, services, energy, and so on. And then in terms of scenarios here, those who are familiar with the Lancet scenario framework, you will obviously see familiar kind of setup here. So what we look into selected set of scenarios focusing on, so we obviously first develop our baseline scenario, which has a number of dimensions, some assumptions how climate would evolve, some dietary dimensions, changes in productivity, food loss and waste assumptions, climate policies. So essentially in the baseline, SSP2 consistent, so shared socioeconomic pathway 2 without any much of an additional effort, let's say mitigation or dietary shifts. And then we have 3 additional scenarios. So first assumes reduction in food loss and waste over time. So halving food loss and waste by 2050. And this is implemented through just tech improvements, right? So we do not cost food loss and waste changes explicitly. And then we have dietary transition scenarios. So that's where the targeted diet is achieved. And on the next slide, I will show you what are the targets that we implement. And then we have the combination of the two. So food loss and waste reduction plus achieving the healthy diet by 2050. So now in the baseline, our caloric consumption, and these are net intakes, they do not change much over time, and that's what their literature also suggests. So for instance, this dashed line is global per capita intake, so they rise from about 2200 to 2300. There is some heterogeneity across regions, but I won't be going into much detail here. And then we have our dietary targets shown here on the right. So this is our baseline kind of caloric intakes, and this is what is targeted in there for the Lancet diet. As you can see, there is quite substantial, these are global averages. As you can see, there is some quite substantial reduction in consumption of meat, poultry and dairy, and also some compositional change, increasing vegetable fruits and nuts consumption, and some slight increase in grains consumption. So think of it of total reduction in caloric consumption and change in composition, much substantial meat consumption and dairy, and in some country cases, increase in vegetables and nuts. So a few slides with an overview of some results that we are getting. So we're looking into a number of dimensions of trends in food loss and waste embodied into trade. So I'll highlight some of them. So first, what we are showing here is we're trying to decompose the drivers that would essentially drive food loss and waste changes over time and across scenarios. So we have here change in population, change in incomes, per capita GDP, change in food consumption per unit of change in food consumption and change in their food loss and waste per unit of food, right? Not surprisingly, knowing the baseline food loss and waste increases in almost all countries. So on average, we see increase of around 50% globally in food loss and waste by 2050. So dietary shift does reduce the growth rate of food loss and waste, but it is not sufficient to contribute to net declines relative to the reference year in 2021. So we also see that, especially in developing countries, pretty substantial growth in populations, like in sub-Saharan Africa, drives substantial increase in food loss and waste. Now, when we implement dietary transition itself, so as I mentioned, it's not sufficient to lead to net declines in food loss and waste, but when we do combine it with food loss and waste specific policies, then we're able to achieve around 63% decline in food loss and waste relative to baseline levels in 2050, and also, net declines relative to 2021. So in terms of composition, we see that halving food loss and waste primarily impacts plant-based food loss and waste. So think of vegetables, fruits, and nuts, which are not that much targeted within dietary transition, right? And while dietary shifts, they primarily reduce animal-based food loss and waste. So we see these complementarities in the two policies, which is also important to highlight. In terms of location, we see that halving food loss and waste primarily benefits farm level stages, given that we have a large amount of land-based food loss and waste generated at farm-based stages, while dietary shifts actually increase farm level losses in selected countries, like in high-income regions. So again, highlighting the complementarity of two policies. So finally, tracing food loss and waste embodied into trade, what we find that with healthy diets, there is high demand for plant-based products within their export kind of embedded food loss and waste, in particular in sub-Saharan Africa, in China, South Asia, so it increases. But reducing food loss and waste within the global dietary transition leads to more significant reductions in food loss and waste embedded in trade, so almost 60%, relatively proportional to what we have in terms of global food loss and waste reductions. And then there are some specific kind of flows that expand or reduce the most, but I won't be focusing on them much here. To conclude, so again, what we find is that dietary shifts alone are not sufficient to bend the curve for food loss and waste reductions, but when combined with food loss and waste specific interventions, we are able to achieve net declines, so around 19-20% relative to reference year and 63% decline relative to baseline level. We also try to identify cases where food loss and waste reduction policies should be combined with specific interventions to upcycle or reuse food loss and waste. So we are highlighting specific commodity stages and countries where could be done. So for instance, in lower income regions, we find that dietary shifts should be combined with tech interventions at the farm gate level, right? So that's where there is a potential to reduce specifically food loss and waste. And finally, very briefly, a few kind of points we're currently working on. So first, we are looking into simulating the food loss and waste reduction through market-based mechanisms. So currently, we assume that it's happening kind of cost-free.
Your time's up.
Good. So one last point. So essentially, costing food loss and waste, identifying food loss and waste reuse potentials, and also testing the hypothesis that food loss and waste shares are constant over time. So that's what is assumed. So we are currently looking to historical data to processes. And I'll stop here.
Okay, thank you very much. And we have a couple of two quick questions for Maxime.
I have a quick one on that your point there about including reuse through circular economy. So I'm just curious how you've thought about adding that to the model, like how you think about cycling things that are waste back as potential input production commodities.
So we are representing this as a selected flows in our input-output type framework, right? So we would have an intermediate input of, let's say, food loss and waste or manure, for instance, as a fertilizer, and then we would shift the production practices so that you have an increase, in the specific flows. But so the tricky point is how do you kind of quantify those and parameterize whether those are costed explicitly or not, and what are the costs of shifting these production practices. So there are some studies that do it at a very kind of granular level in specific commodity and specific countries, but the challenge is how do you expand it to more like country-wide and then global-wide and commodity-wide. So that's the main challenge we are currently facing.
Somebody else?
Do you see any effects on environmental aspects like GHG emissions? Like combining these two, do they have net reduction?
Yeah, we do have there is a decline obviously in GHG emissions, and partly because the food production declines, right? So when you have food loss and waste reduction policy, essentially your food availability increases, right? And then food production declines, and you have a reduction in associated environmental footprint. So we do have estimates for emissions, for instance, and their pollutants.
Great.
Now the question is whether the actual implementation costs. What would be the actual implementation cost of those reductions? Yeah. But we do have the quantifications of, you can say, benefits, right? So that's kind of the first step, and then if you have costs, you can do the cost benefit kind of calculation. Let's say.
Good, very good. Thank you very much. We're basically back on time now. Siwa, can you hear us?
Yes, I can. Can you hear me?
Yep, loud and clear. So we have a really an old colleague of most of us here, Siwa Msangi, from USDA, and he's going to present to us on the importance of aquaculture in global analysis of food and energy futures. So, Siwa, the floor is yours.
Thank you.
Yeah.
Thank you. I'm sorry not to be there in person. You can see my slides, okay?
We do.
Okay, great. Yes, but you can see I have my gold economic modeling team cap on, so I'm with you in spirit, even if I'm not there in El Batan. Maybe, hopefully, the next time. Oh, sorry. Let me advance my slides here. So the motivation for what I'm going to do today is, in the past couple of years, as you mentioned, I was at IFPRI for a long time. I've been revisiting some of the agricultural market projections I used to do in order to try and give some better linkage to some sectors that were not well connected before. And again, this is not impugning any of the models that I worked on, but I'm sure many of you are aware of the challenges of when you do project funding driven research, something that's specifically for one piece and not another piece. Sometimes you don't always have the luxury of being able to connect all the dots together in the way that you normally would like to. So I guess I'm taking another bite at the apple and trying to connect things. And my experience, again, with the impact model has been such that when you do one project, for instance, in the when the food price crisis was unfolding and we were trying to do a lot of biofuels analysis, we did that sector as best we could, but there was a lot that we didn't do fully in terms of like the market for co-products, and we kind of tried to displace livestock feed from corn with other things in a rough way, but not really in the way that you could have done it if you had a little bit more time and a little bit more resources. But we actually did end up doing another study on livestock that was more detailed. And Mario, of course, you're very familiar with this because we did it with you using inputs from the ruminant model and sort of paralleling what you did with Globium. And that greatly improved the livestock side. But of course, that was focused on livestock. We simplified away just for getting things narrowed down, the biofuel side. And of course, we didn't have fish in it. And by the time we did do the fish study later on, we ended up again with we only had like $50,000 or maybe $60,000 from the World Bank. So we ended up just simplifying the other two around and focusing on that sector. And we learned a lot out of it. All of these ones gave us a lot of insight, moved the model forward, but you don't quite get everything in the same place linked together in the way that you'd like to. And that's just the nature. That's the nature of the business. And I think many of you in the room recognize that. So after leaving it free and going working on the GCAM model for a bit, there was a need. We felt the need that we wanted to improve also the substitution for feed for livestock coming from biofuels in a more realistic way. And so this actually allowed me to sort of revisit this whole issue again and to think about, what's really important when you're trying to measure the environmental impact of something like ethanol production, which, as many of you know, has land use change effects that come both from what's produced and by the other co-products that are being produced and what gets displaced and how that figures out on the landscape. So we were trying to get a better handle of that and achieve a better representation of feed replacement. And that whole process of now moving to another model, but still thinking about some of the same issues, got me to go back and rethink how to better handle the feed allocation overall. Even in the context of a different model, but I think some of the same basic issues are the same no matter what you do. So I started, where I usually try to start with a simplified model where you're just trying to get to the basics of what you're trying to get at. And then I realized later, and I'll show you sort of that revelation, that aquaculture also needed to be a part of that picture in order to get things working correctly. So just to give you sort of a schematic of how these things are laid out, and I know this is familiar to a lot of you who do this kind of modeling, but so you have just on your crop side, you have a production side, you have a demand side, you have to connect those two with trade, and there's price formation, and you link your regional prices to your world prices, and there's feedbacks that go into that. And one of the key things that you want to do for the livestock side is, of course, make sure that the number of animals that you have is driving what's going on the feed side. Now, some models have fixed feed ratios, and I've worked with those for a long time as well. But if you go a little bit more and you try and make those flexible so you can actually substitute, it's not necessarily always the same ratio happening for each animal. But in order to do that, though, and to be cognizant of the biophysical reality of what the animals need, you also need to make sure it's not just a quantity balance, but it's also a nutrient balance for those animals, that the energy and protein that they need for the herd is balanced in terms of what you're providing them. And what the work that we did with Mario, of course, the ruminant model was doing the heavy lifting in terms of telling us what was needed for the animals. And we sort of conformed to those diets, but there's other ways you can do it. And I've been sort of going back to some basic NRC equations to try and calculate the energy protein for different, whether it's, lactation or sort of different things, maintenance of animals, to try and get an actual sense of what's needed. So that's, of course, a key element of if you want to do substitution in a realistic way. And most ag model, pretty much all ag sector models have some sort of a process sector. And in the case of any model that has animals in it that consume those co-products like meal from soybean crush, it could be safflower crush or any of the other oil seeds. That's a necessary sector to have. And of course, you have your drivers that drive you into the future. And so I think looking at this is very familiar to most of you. Most models would have this kind of side. But now if you wanted to go a little bit further and connect that to a biofuel sector, then of course now it has to have its own sort of side to it where you have production driven by the availability of feedstocks from the ag side. There's a conversion technology that's connecting those two. And of course, what's most relevant for the livestock side, and of course, the biofuel side also has its own exogenous drivers in terms of the blending policies, in terms of what an oil price could be. So you need to have all of those there. But in terms of what's necessary for the feed side of livestock, it's that conversion technology that produces co-products like the dry distillers grains and solubles, which is important for the U.S. feed market. And Impact had that. The model I'm currently working with also has that as a result of wet and dry milling of the corn sector. So you need to have that as part of it. And so you get the basics of this, and so so building again, sort of from scratch, rethinking everything, putting it together. I did something that I haven't done as much in the past, is that you try and then simulate your model forward and see how it compares to actual data, which is something we should all do. Sometimes we don't always do it in the same way. So anyway, you start from year 2000, you go forward, and okay, you're a little bit off, but at least your trends of ethanol production and use are more or less in line. So that's a little bit encouraging. Okay, maybe you might miss a few of the dips that happen in the net export trends, but at least things are going in the direction that you'd expect. And so at least you have a little bit of confidence in terms of how that market's working. Looking at the price ratios, and that's something I've discovered I need to do more of, is especially for ethanol corn price ratio. If you're doing about livestock, maybe the live weight price of a feeder cattle and its feed is another price ratio you should have. So also looking at that, again, you might not capture all the little dips and turns, but at least you want to be sure that at least your trends are going in the right direction. So that was that. Yeah, at least that was encouraging. At least this experiment was working well, and that things were building out the way that they should. However, then when you got to the market for the co-products itself, there was a bit of a incongruity, let's say. So the production was okay, but then you just didn't get the exports that you should have because you're overestimating, of course, the feed use. So there basically is not enough feed use of DDGS in the US to match what's there, or that matches what's there, and that would give you the exports that you actually see in the data. And it was at this point that I realized that since so much of there's a good sizable portion of US DDGS exports that go to Southeast Asia for biofuels. And so by adding then, sorry, not for biofuels, for aquaculture. So the aquaculture, the demand for protein-based feeds in Southeast Asia and elsewhere, it was one of the key drivers that wasn't in previous analyses that we did and needed to be in this analysis in order to even get anywhere close to where you should be in terms of the market connection between the co-product markets for DDGS and what's happening abroad. So that was the revelation that sort of got me to think that actually I needed to have all three of those projects working together. But again, as I mentioned, sometimes you don't always get that luxury until you go back and look at things more carefully again. And so, and of course, to get a global fish model, it has its own complexities to it. I mean, you have both the aquaculture and the capture side. The aquaculture is incredibly dynamic. That's actually in the 2030 study that we did at IFPRI was the one that was the most dynamic, that we spent the most time on. Of course, you want to have the same macroeconomic drivers for both for all sectors driving the demand, regardless of whether it's for livestock or food or for fish and fish oil and meal. And you also and we also discovered that we would make the capture sector growth exogenous, because really that's not the sector that's been responding the most to growing seafood demand in the world. So by having that element and going a little bit, so the 2030 study went to 2030, but we've some further projections have been done, and that's where the starting point is for further work in order to be able to connect this. And as you can see, it's just really highly dynamic. And I haven't given you a regional breakdown, but as you can imagine, most of the action happening in the aquaculture sector is in Asia. And that's one of the exciting and challenging things about the aquaculture sector, is that it is very, very, very dynamic. The 2003 study of IFPRI, the 2020 results were already where the 2020 results for that study were already where the 2010 numbers were when we started doing the 2013 study. So I think aquaculture is a sector that you need pretty much every 10 years, at least, you need to go back and revisit it. So I think I'm overdue for doing that's why I'm sort of looking at this again, because I think probably there's a lot that's changed that we should probably be aware of. So
see what 1 minute? 1 minute?
Yeah, so there's ongoing work. We're going to link now. So I'm going to try and distill down the fish model and get it a little bit more simple, so we can link it with the other model that I showed you and see what those results are. We're starting that process to basically to see what effect it's going to have when you try to do shocks and see what happens to the land base, especially as a result of some of the shifts that we would expect from indirect land use change for biofuels. And as you can see from what I showed you, the rapid expansion of aquaculture allows you to absorb some of those co-products way more easily than the livestock sector can, because it's happening so fast. And so it's really my feeling that any evaluation that you're going to do without having that there is going to probably bias what your results would be. And so that's why I'm coming back to the realization that aquaculture really needs to be part of the global modeling that we do. And I think having more people on this, maybe there'll be an AgMIP for aquaculture coming up, and I think that's well worth it, and I think it'll be rewarding for everyone who does that. So thank you for your attention, and look forward to your questions.
Thank you very much, Siwa. That was really insightful. Any questions? Don't be shy. Come on, baby. Or is it ignorance about fish? Yes.
I could just
Matt.
just a quick technical question. I'm just curious how you treat coal products directly in the model, like as a production, as a sector that produces multiple things. Like, was that something new? Is that something you've been doing for a long time? How did you conceptualize sectors that could produce multiple products?
Well, so actually in the model that I'm working on right now, which is a US focused model, like for instance, the corn sector has, wet and dry milling. So you get both DDGS as a co-product, you have gluten feed, gluten meal, you have corn oil. And each one of those have to have their own markets. They have to clear and they have their own demand side. Some of it is processing demand, some of it is food demand. And so so all of those have to be endogenized in order for it to work correctly. And so you take engineering coefficients essentially to sort of look at the conversions, but then there's always a bit of a balancing that you have to do to make sure that at the end of the day you're matching the supply and demand in the way that you should. And again, getting those looking at the prices and the price ratios is an important way to tune those sectors.
And Siwa,
Yes.
is there any way of doing like an aquaculture module that is not model specific, but that you could actually plug into, you start with thinking of impact, but can the same structure be taken, I don't know, by Magpie or by Image or any other model, so that everybody can actually start having an aquaculture sector more explicitly in their models? Or what's the way to go about this? Because I've heard about aquaculture now for 15 years at least.
Yes.
And you've made great inroads into all of this, but it would be good to hear, how should you think we should attack this problem?
I think start simple. Those elements that I showed you are kind of essential. You kind of have to have the fish meal, fish oil as its own dynamic sector alongside the aquaculture sector. And again, you don't lose much by keeping capture exogenous. I think there's a way to make sort of a generic model that people can use. FAO is, I think, one of perhaps the other group that now does regular fish projections along with the other elements of the outlook. How closely they've linked it to the other parts of AgLink Cosimo, I'm not sure. I would encourage them to do so because I think they're going to get a lot more insight if it's deeply embedded versus if it's just kind of a parallel module that you run on the side. But that'll be something, it can be in GAMS, it can be in Julia. There's the language, might drive in terms of who's going to use it, but I think you can do it in a way that would be generically fit most models.
Great. Okay. Thank you very much. I think that we've exhausted the time, so thanks a lot. Now we're going to go to Ron. Ron, can you hear us?
Yeah, I can hear you fine. Can you hear me okay?
Yeah, we hear you really well. Thank you very much.
Okay, great. Thanks, Mario. So my talk today is about a modeling effort that's been ongoing for a few years now. It's joint between the Wisconsin National Data Consortium with Tom Rutherford and also the folks at GTAP. And also here at the Economic Research Service, and my collaborator here at ERS is Shelley Suttles. So some of the themes that were brought up in the first talk will come up here as well. But I also want to mention that I grew up 3 miles from the St. Paul campus at the U of Minnesota. So I always like to hear what's going on in Minnesota. So the modeling framework, I've been calling it the Global State Modeling Framework for Agriculture. It's also called the GTAP WinDC model for the groups at Purdue and Wisconsin. And so part of the goal here is to, in the spirit of global and regional assessments, or linking global and regional assessments, which is sort of a perpetual AgMIP goal, is to make some progress towards bridging the gap between global and subnational analysis, and to develop a modeling framework that links global change at the world level with subnational activities in the United States. So the goal is ambitious here, and to be able to deal with all sorts of drivers of global change like population, income growth, agricultural productivity growth, dietary preference, climate change impacts in agriculture, and also interaction with agriculture, bioenergy, and climate change mitigation. So assuming we're successful, there's a whole wide range of applications for this type of framework. So I'm going to give you a sense today of where we're at on this in terms of developing this model framework. So just a little bit about the GTAP WinDC model. Again, it's joint model development. It starts, if you look at the top-down version, it starts with the GTAP set of world regions up to 160. And then sort of downscaling down to 50 US states within the US region. You can also look at it from a bottom-up perspective if you're just working with the US, and that's sort of what the folks at Wisconsin are doing is working with a lot of the data sets from Department of Commerce to look at income distribution, input-output relationships from the 2017 detailed input-output table from the Bureau of Economic Analysis and build up to the US level. And so there is the challenge of how you link these two approaches in a consistent way. And I'll also try and show a couple of sample applications, very stylized at the moment. One is US ethanol expansion, and the other is food shocks. So in addition to this GTAP WinDC effort, I've been building this future agricultural resources model for the past decade or so, and I'm one of the 10 modeling groups that participates in the AgMIP global economic activities. And, for AgMIP, we generally work with 13 world regions. In the farm model, I've got 38 production sectors to cover primary and secondary agriculture, as well as primary and secondary energy. It's got 5-year time steps through 2100. I think the main challenge, for this type of modeling, for all the modeling groups, is to have consistency between economic units that are in the social accounting matrices or the input-output tables, and linking those up to physical units, whether that ends up being tons or calories, or on the energy side, whether it's joules. So some of the activities that the farm model's been involved in are of course, AgMIP studies, Stanford Energy Modeling Forum. Bioenergy plays a huge role in a lot of the mitigation scenarios. And so the most recent report from the farm models, one you see on the right here, you can download it if you want from the Economic Research Service website. But that gives a nice application of the farm model, trying to define, what is the size of the global agricultural system and what kind of units do you use? So I use crop calories for the basic units, which turns out very convenient. Calories are convenient for comparing across food calories, crop calories, or different kinds of agricultural products. So the next step, how can I create a new version of farm that disaggregates the US region into states or groups of states? And so what we end up with is a nested US state level model within the global GTAP CGE framework. And I'm working at a top-down sort of approach where I use the GTAP numbers, especially the trade numbers, as sort of, I'm not going to change those. And then I take activity levels for each of the production sectors across the 50 states and disaggregate it algebraically to the different states. So one advantage of having state level production is now we've got a production function for all of the crops in each state. So it's makes it a little bit easier to link up to, say, output from crop models. When you're working at the national level, we're taking all this detailed crop modeling at very specific geographic locations and aggregating into one number for the US or for the other regions. And, that's not terribly satisfying intellectually for either us or the crop modelers to see that done. So here's a schematic of, the way sort of GTAP trade is set up. You've got these world regions that trade with each other, and they trade with the U.S. And so they see what the U.S. imports and what the U.S. exports. Now, in this this model with the states broken out, on the left, the rest of GTAP has no idea what's going on actually within the U.S. region, but the U.S. region is built out into states, and the states actually trade at a national market. And so that's a simplification. And I think that was mentioned earlier, maybe by Dominique. It was that Tom Rutherford and others are working on how you have bilateral trade among states, how you do that calibration, and so on. That's a tough job, and so they're working on that. But I'm sticking with this sort of simplified approach where the states trade through this national market. So these are the 13 AgMIP regions on the left, and then on the right you see the different sectors in the farm model. You can see I've kept all the GTAP sectoral detail for primary agriculture, food processing, primary energy transformation, and energy intensive industry, so that I can do applications that talk to both the energy side and the agricultural side and how they interact. So the first application, sample application I'm going to talk about is ethanol expansion in the US. And these are just some data, some historical data as to 3 major types of biofuels in the US: renewable diesel, biodiesel, and ethanol. And you can see that consumption by state, roughly follows population, which I guess isn't the big surprise. California may have some more incentives for using biofuels than some of the other states, but also there are a lot of people there. But biofuel production is really concentrated in the Corn Belt, states like Iowa, Illinois, Nebraska, Minnesota, South Dakota. So you've got this difference between where things are produced and where they're consumed. So this first sample, I ran this really simple counterfactual. This is all comparative static. At some point, I'll try to have this step through time. But I put a 40% ethanol subsidy in the US on ethanol. And what I've done to simplify this a little bit is I am working with 9 groups of states, 9 subregions in the US. You can see those here. And also just 4 world regions: the US, rest of the world, Mexico, and Canada. So that brings the model runtime down to a few seconds. And so it's really easy to make changes and do other things, but you can expand it at some later date. So corn ethanol production increases by 18%. And because of the link to input for maize or corn in the US, you see that production increasing as well. But there's also feedback to the rest of the world that due to this incentive, we also have a little bit of feedback to production in coarse grains in the rest of the world. Just one thing to note about these 9 world regions: these are the Forest Service, U.S. Forest Service world regions. I was thinking, well, maybe at some point in the future, I want to talk more about carbon sequestration in forests. So I just sort of use those. But the North Central region is actually a pretty good representative of the Corn Belt. Now at AgMIP10, a year and a half ago, we had some presentations. I tried to give one as well on food shocks, and where we had the food shocks coming from the rest of the world to the US. Well, I'm doing sort of the opposite here in this counterfactual. I've got a 10% decline in total factor productivity of coarse grains in 2 of the US subregions, North Central and Great Plains. And you can see in the plot on the right, there's a decrease in consumption there. But because the market impacts the other subregions in the US and other world regions, to try to make up for that difference. Okay, so this is my last slide. Where am I at on this? I've got this, I guess I sort of call this a canonical model. It it does have something beyond just the basic data. I did need to create markets for personal automobile transportation that would use more ethanol blended into the fuel in the ethanol subsidy case, and also co-products. DDGS is a co-product as well. So the framework is actually coded here in this dialect of GAMS called MPSGE. It's a syntax that allows you to build and modify models quite quickly and handle greater levels of complexity. I realize the complexity here is getting to be pretty tough, that you've got all these different dimensions to deal with. And I actually forced myself to learn MPSGE to deal with the complexity here. So next steps, get the time steps in, get the energy quantities in, introduce some more energy technologies, doing documentation right now, writing a technical bulletin on the model for ERS, and then there will be a research report to be a backcasting exercise with ethanol. But one final note is this disaggregation or downscaling could be done for any country in the GTAP database into subnational units if someone has the energy and data for states in Mexico or wherever. That could be done as well. So I will stop there. That's an overview of
Thanks, Ron.
what I'm doing. Yeah.
Great. Ed, a couple of quick questions for Ron. Yes, please.
I have a quick question. Thanks, Ron. This is Maxim from Purdue. I was wondering, have you thought about how do you trace, food and nutrition in this framework for U.S. states? I mean, is there specific, I don't know, state-based food balance sheets, or do you downscale national averages? What are your thoughts in this area?
Yeah, that's a good question. Right now, I'm just downscaling the national average, and for things like that, I'm basically using either population or a gross state product to do something like that. But if there are data available, and it will become more important if we start talking about income distributions. The folks at Wisconsin at Winn-Dixie have been working with income quintiles, 5 types of income levels. But basically, it's taking what's being done at the national level for GTAP and the consumer demand system that I have there, and just scaling it by activity levels to the different states. So yeah, there's a lot more to be done if data are available there. And I can't remember. Did you have another question, Maxime, or was that
No, that's it. Thanks. Yeah.
Okay, somebody else? No? Okay, so Ron, thanks a lot. Super interesting. We're going to move, and now we're going to have Donna presenting.
So it's just, yeah. Okay, that's amazing. Okay, ready? Hello everyone. My name is Donna Hennessy. I'm a research fellow at the University of Oxford, and I'm in the food systems group under Marcus Springman. And what I'm presenting on today is the use of agri-economic models in food system analysis, a multi-model contrast of data sets and aggregations. So I wasn't very sure of the caliber of people I was presenting to. So the first slide is really just the current situation, and I'll blow through this fast. The food system is a large, varied, and complex system, and that's why we build food system models, to do the calculations and the thoughts that one person cannot really do. They're also very important tools for studying economic and agricultural implications of changes, of shocks, of just playing around and understanding what could be occurring. But but food system models have been built by different institutes for different reasons. They have different compositions and they have different outcomes. And as a result, they treat their food supply, they treat their food demand and production rather differently. And that is kind of what I'm going to be focusing on today. And lastly, food system models are increasingly used to provide outputs for nutrition and health-based analysis tied with environmental impacts of food systems. And from a dietary perspective, this requires rather granular level detail outlining consumption and production at as minute a level as possible to really just help us demonstrate the positive health impacts of dietary change. And at the moment, it's primarily just an output calculation. These are just papers that I did a quick search on because once again, I wasn't sure the caliber that I was dealing with. So I can just zoom past this. So what I want to focus on today is that what has been very handy with the EL2 work has been that there has been a cross-model validation of the Eat Lancet.
Yeah, EL2 is the second Eat Lancet assessment.
Okay, my apologies. And what has been very, very interesting about this is that it has been validated by a selection of global food system models. And they have come together and they have provided a base year analysis, a business as usual scenario that everyone has agreed to. And they have provided they have provided a broad data cube of results aggregated under the same structure, which actually allows for a momentary insight into how all of these food system models are structured and how their food system structures actually create differences between their results. Now, I'm not saying that difference in results is a bad thing. We want food system models to show us different things so that we can genuinely get a broad picture of what is occurring. But in a base year, in a baseline scenario, we would hope that there is some sort of alignment. So I'm going to compare the 7 regions and the 25 products of AgMIP against the data sets that are available. And if I have time, I will contrast that against the FOFA data sets that I planned for 13 minutes. So what we are looking at is these are the models that were used in the analysis. So I've just gone through them briefly. There they are on the left. They're global food system models, CGE and PE models. I've outlined where they. Oh, I should say now that I did this work by conducting a literature review of the model documentation and their user manuals. And many people have pointed out to me already today in the last few days that that is out of date. So some of this might be a bit inaccurate. So their food databases all generally come from the food balance sheets or from GTAP. And except for Capri, and that is because Capri is generally a European Union based model. So they use a lot of EU data, EU consumptions. So they come from the same 2 main databases, but their the most recent food demand from them have varying years of inputs rather than an agreed one. So then what is happening is with a 2020 baseline, we might be forecasting slightly towards it. The range of years for the baseline food demand ranges from current year all the way back to 2000 for certain models. And then they use their forecast methodology to come up to the baseline. The food group aggregates, this is just a list of food groups that occur that have been used for dietary-based analysis. We see a range from a low of 8 all the way up to 56. The 43 that is in Capri, that is actually a bit of an illusion because once again, they have a lot for Europe. And then when they go outside of Europe, their number decreases. But as we can see, when it comes to, we've got crop aggregate, livestock aggregate, and processed food products. And what we can see is that the food balance sheets outlines about 97 different food groups. So what we can see is that we see a fast winnowing down of the numbers. And as we winnow down, we aggregate food crops and food products together, and we lose some of the granularity that from a dietary perspective we might enjoy. So this is this is the food demand. Oh, I need to go back. And this is how they aggregate their regions. So unlike with the food demand where they clearly outline their reasons for winnowing down, and it is usually due to model restrictions or the need for aggregation for certain model inputs. The reporting regions is usually done by the philosophy of the model. That is incorrect. That should be 14. But generally what we have is that we have a selection of regions that go all the way from a low of 10, which is MAGPIE is an aggregate of biophysical, all the way up to 159, that is an impact. These are the reporting regions for calculating inputs, for calculating yields, for calculating many components. Models use very, very wide and disaggregated sets. But generally what drives the decision of the reporting regions is the decision of the model builder. So for instance, AIM, which is out of Japan, they have Japan. Capri obviously distinguishes every European state. But then if we go down to say like Impact tries to do every state in the world, while then we generally see in a lot of models larger geospatial driven ones to just ensure that results are fairly homogenized, but also they're based on their environmental impacts. Then we also include price elasticity, because when it comes to consumption and consumption choice, a lot of the dietary and food demand and income components come in on the input region level, but also the choice in food consumption comes in on the region level as well. So region level decisions are very much driven in this manner. And what we can see is that they come from a wide variety of data sources, and they have a wide range of ages as well. And they can have very deep data sets. So for instance, MAGPIE has a historical data set going back from 2014 and for every country tied to FAO data sets, while others can be rather shallow, like GloBiome has a 10-year data set that is based on US consumption and consumption pattern changes with growth in GDP. So then just the forecasting methodology. Most of the models use their own elasticities that are either they can decide them to be fixed or dynamic. Most of them generally have a choice of switching, and a lot of them generally go dynamic. But then many make allusions to FOFA targets for certain products like red meat and other certain products as well. And this just generally drives a lot of decision-making processes. So we've outlined how the foods are aggregated, and we've outlined the logic behind regional aggregations. And what I'm going to briefly show you is the distance of the baseline year from what the FAO said was occurring in 2020 from an all-model mean. So in the gold bar is kilocal per capita consumption at a world level. The FAO said that in 2020 we were consuming 2,548 kilocal per person per day. And in the slate bar is just total production total production of the food products. At the bottom, we have the different aggregate groupings, and the error bar is the distance in variation between the models reporting. So one of the big things is when we factor in the actual error bars, the food system model ensemble actually rather matches well with the FAO value, except for aggregate animal source food. And I have ideas on why that is. The lowest variation between the models is occurring in grains, which makes sense because with your food groupings in all of your models, you will frequently bundle a lot of food products together in another category, while the grains usually have a singular one, even down to wheat, rice, and maize. But what we can also see is that with vegetable, fruits, and nuts, we have a very large variation between the models, both in food consumption and also in food production. And also we have large variation in the production of milk. But when we're talking about this from a dietary perspective, a very large variation like that means that using like footprint values or trying to derive distance from a baseline year, it can be very difficult if the model doesn't closely align to the year that it is stating is its baseline. So that is what it looks like in consumption. And then I decided to show it out by regions. And this is just for aggregate crops, aggregate grains, aggregate veg, fruits, and nuts using the regions that AgMIP provided for aggregation. So once again, the data sets, the models had regions from 159 all the way to 10, but AgMIP has brought it up to 7. And what we can see is at a world level, once again, very close and very tight in the variation, especially in grains. But once again, with vegetable, fruits, and nuts, which is a food product that we prize highly in dietary-based analysis, we can see very large variation between all of the regions. And we can also see that we have over and under production as well. And this is two things are going on here, which is one, it is just disagreement between the models, but two, it is also the aggregation up into the AgMIP data set. So many of the regions that are provided by certain models, like once again, say Magpie, they are composites of countries. It can be brought down to a cellular level, but those cellular levels, the 200 cells that go into Magpie, don't perfectly align with country structures. So I think this might also just be a little bit of static from the analysis. But then we decided to look at the greenhouse gas emissions of the same products across the regions. And what we can see is that certain regions, and once again with certain products, this time with animal source foods, we can see that there is rather close alignment except for some regions. And then with aggregate crops, we can see that there's a very large variation as well. So if we're talking about trying to do, say, some dietary informed footprinting, where we try and tie food consumption to the field of production and use environmental footprints, using different models could lead to very different and varying results. 1 minute. Okay, I'll blast through this. We don't need the discussion baseline because I've been discussing that. When we try and compare it against forecasting business as usual, what we can see is this is now compared against the Future of Food and Agriculture data sets that were put out by the FAO back in 2008. And this is once again a percentage of it. We can see that there is closer alignment to FOFA in the 15 yearly increments up to 2015, and that we can actually see that variation, while it is rather high, once again, closest in grains, there is actually kind of a linear relationship, and that's just the distance in time. There's an inversion in ruminant and non-ruminant consumption, but that just comes into line with the aggregate animal source food. And once again, from a dietary perspective, the switch between the food types can be a little bit, can really throw calculations and can really throw understanding of forecasts. And once again, when we look at production by production, we can see that there's very large variation. And once again, it comes into alignment with the FOFA calculations. But once again, this is just the distance between the models. And this is just an all model ensemble average. We don't expect you to match going out to 2050, but this kind of comes into that maybe from a dietary perspective, we need to build something that is modular and can be pushed in with your models rather than actually as a post-model output calculation, because there can be very large variation between all of these. So that's a QR code to the food systems group that I'm part of. I've got a team member in the back if you want to talk biodiversity. But food system structures and their underlying data sets generate a high level of variance when we look at an all model mean. But in certain products, there is nice aggregation and low variance in certain products like grains, which means that we're actually rather hopeful that something similar could be done with vegetable, fruits, and nuts, which are very important. Regional aggregation generates high variance across food groups, and that's just nuts. I don't know how to provide a practical solution for that. That's just the aggregation methodology, I'm pretty sure of. And studies using dietary-derived health impacts in dietary and environmental footprints may be hindered by variance between models if we wish to perform some sort of cross-model analysis. So especially if we feed all the way back through the model structures and food production. So still very raw, but this is where I'm heading at. So thank you, and any questions or comments?
I'm sure there must be comments, questions. Daniel? Daniel at Cornell University. Have you taken a look at what those look like for oil seeds and pulses? Because one of the big issues with vegetable fruits and nuts is that the different models, that category is often a residual. And so what's in vegetable fruits and nuts can vary dramatically from one model to another. So like when we were looking at some of these things, we saw once you added up vegetable fruits and nuts and oil seeds, and then did that as well on the FAO side, that explained a lot of the deviations, because sometimes pulses get mapped into vegetable fruits and nuts, sometimes they get shoved into oil seeds, sometimes they get shoved into pulses on their own. So there's a bit of a challenge of just making sure that you're actually comparing the same things to each other. And I don't know if you've had a chance to look at them.
Yeah, so I've had plenty of time to look at them, and that's actually why I decided to show the aggregate veg, fruits, and nuts. Because if you, as you said, if you look at the individual crops, so in the AgMIP data cube, you were allowed to state up to about 25 different crops, and many crops and livestock systems, and many people did. And when you go down that route with the people who state it precisely, yes, you can get up to it quite well. And also there are certain models that differentiate between vegetable, fruits, and nuts, and they can closely align. But some model, and then there is obviously the aggregate other crop, and the variance in that was absolutely huge because it is a dumping ground. But I decided to show the aggregate vegetable, fruits, and nuts in this because from a diet and health perspective, if you're coming out and saying this is aggregate vegetable, fruits, and nuts, and then there is a very high variance, it can lead to a bit of confusion. And also there was quite a high variance in oil seeds between models as well. So it's not a perfect solution, but it's.
So you might want to try doing the aggregate up on FAO site, and then aggregate up so that you can see if at least if you added up oil seeds and vegetable fruits and nuts, does that look like it adds up to oil seeds plus vegetable fruits and nuts on the FAO side? Because then you could sort of see at least, is it that the models aggregate things separately than the way that they're done, the way that you're aggregating from FAO? Or if it's, then you could control a little bit to see whether or not it's just where things are being mapped within the models to just test it, because there almost certainly will be differences. But how much of it is because of, one model vegetables are shoved into other categories, which happened in some of the models, versus this is because the actual calorie content is wrong, versus it just being mapped somewhere differently.
So you are correct, and I should definitely do that. Well, definitely double check that. And
you kind of get that with the old crops, right?
Yeah.
You see that they do align fairly well. And so it would be interesting to see if you can do it on some of the others to kind of capture how much of it's an aggregation composition kind of remnant versus it being that the data sets are giving you different numbers.
That's definitely true. And some models have put in, as we were saying, ag other, and that can be almost majority of the ag crops colors. Yes.
Thanks a lot. Thanks.
Okay.
We need to move. I think that this is an important conversation to follow up over lunch or something like that. Great, Maxime.
Yes. Yeah.
Again,
Yeah. Oh, great, thanks. I'll try to stay brief since lunch is on agenda. So this is another study that is a spin-off from their Lancet set of studies. And here we are looking into impacts of dietary transition on trade. So, there have been a number of deep dives looking into different dimensions of dietary transition, but not that much focusing on trade. So we decided to look more into this specific dimension. Earlier, the literature looked largely into what could be the implications of some trade policies on food security, for instance, trade liberalization, or what other, impacts of existing non-tariff barriers on food availability and affordability. In general, what studies have been finding is that the cost of the existing trade barriers are not that large in terms of dietary affordability, so somewhere between 1% and 2%, depending on countries. Few studies have looked into the implications of dietary transition on trade, but focusing on specific regions. For instance, there was this Giebel et al. 2021 paper looking into, changing meat demand in OECD countries and identifying some spillovers in the rest of the world, but not so much in the global dietary transition context. So that's essentially where we are heading here. Methodological framework, I won't discuss in detail. So we're using the same global TG model envisaged. So the features I have already mentioned. On the scenario side here, we are looking at a bit different set of scenarios compared to the ones that I presented in the previous paper. So since our focus here is not so much on food loss and waste, we are focusing more on, obviously, baseline is the same, but then we are looking into different dimensions of dietary transition and agricultural kind of development over time. So we have one scenario with higher agricultural productivity. We have scenario where diet is achieved without any additional levers. We have also waste reduction scenario here. We have climate policies and aspect, and then we have the seed Lancet dietary transition scenario, which essentially combines all of this together. So in this way, we're able to decompose the impacts of different channels on their kind of aggregate results. So I will start with a brief overview of how trade patterns evolve in the baseline. And so what we find here is that, well, as the food demand somewhat expands over time, we see also an expansion in trade, but trades to total food consumption ratio actually marginally declines at the global level. So this red line, so we see, import to total consumption kind of is around 15% in the reference year, and it declines to around 14%. So you can say roughly stay constant, and across countries trends do not really move that much. So import dependency marginally declines over time, but in general stays the same, right? In terms of the composition of trade, we also see some kind of marginal changes over time. So for instance, sugar crops seems to become a bit more traded over time. Also some grains, slight expansion in ruminant meat, but not that much as in, for instance, sugar crops or oil seeds. And overall, we see this growing trend. So for instance, we see that trade in crops increases by around 1%, and trade in ruminant meat declines by around 1%. But again, no, the trend seems to be pretty kind of stable over time in the baseline scenario, right? So that would be our starting point on which we would be imposing our dietary kind of transition. So in the previous presentation, I put a table of dietary targets here. It's similar representation, but now with bar charts. So, and it might give you a bit better idea of the scope of kind of interventions we're looking into. So blue charts represent reference consumption in terms of gross per capita per day, and red or green bars represent kind of our dietary targets. So red target is like an upper bound, for instance, that we should have to achieve the diet. So in case of sugar crops, we need to reduce consumption by 76%, for instance, cattle meat by 64%, other animals products by around 60%. For instance, for vegetables and nuts, globally, we are already kind of above the lower bound, so not much adjustment is needed there. Again, it's globally on the country level, we do have some variations. So what happens to trade when we implement the dietary targets? So first, we see that there is a decline in trade, overall decline, and that's driven simply by the decline in food demand. So because with dietary target, we both change composition, but also we change the net intakes, and we have some productivity improvements there as well. So overall food demand declines, so imports and global trade also declines. At the same time, we see there is a relocation of trade. And to achieve some of the dietary targets, some countries need to import more food, for instance, vegetable fruits and nuts. So the overall import dependency increases. So there is decline in trade, and increase in import dependency. It differs across countries. So for instance, we do not see much changes in import dependency for China, while for US and for middle income countries, we see higher changes in import dependency. By for instance, in US, by around 12-14 percentage points. And the blue bars represent the impact of dietary transition per se. Other bars represent other channels. So we see that in most cases, it's purely dietary transition that is essentially driving this result. But at the same time, we find that in some cases, for instance, in middle income countries, so mitigation efforts might also interact with it. And in most cases, mitigation efforts essentially decrease import dependency. So there is this also interactive channel. So this is another chart that represents import dependency. But now, so import dependency, there is a question, how do you measure import dependency? So you can use different units. You can use calories, you can use dollars, you can use tons. And what we find is depending on units of valuation, results might change. So which is important aspect. For instance, many PE models, they would use kind of volumes, while, for instance, economic models they would use primarily value currency. So here we see that some results might change depending on kind of what valuation unit you use. So for instance, when we use tons, we find that in a number of cases, this red part of the bar represents essentially reduction in import dependency, while when we're using pure currency, we see that in almost all cases, import dependency increases. So, and then we can decompose it across commodities. I won't be discussing much into how kind of trade relocates across countries, but just to note a few kind of points is that we see that in most reduction in import sourcing are associated with exports from high-income countries, including Europe and US, to middle and low-income countries. So that's where the trade relocation is happening. And most of these reductions are also associated with declines in exports of meat, sugar crops, dairy commodities. We do see some expansions in trade flows. So for instance, we see an expansion in exports of food from Russia to India, from US to China. So there are selected flows that do benefit from dietary transition. These are mostly vegetables and nuts exports, but also some crops. So that's what's happening, but also major declines, for instance, for Brazil. For Brazil, for instance, soybean exports to China declines quite substantially due to the reduction in meat demand. Then one last indicator, so we looked into is trade balance and also trade diversity, right? So in terms of trade balance, we see that in dietary scenario, export of food products primarily rise in lower income regions, and in some countries might become large net exporters, for instance. So for instance, this is the case for former Soviet Union countries. They become net exporters, and also a case for Southeast Asia as an example. And finally, the last dimension we looked into was import diversity. How did we measure it? We use this Shannon entropy type index. So essentially, if your imports are equally distributed across commodities and sources, so all shares are equal, the unit is 1. If you're importing one commodity from only one source and do not import anything else, that's like 0, right? So we looked into how these shares change under the dietary transition scenario. We find some mixed trends. And in general, it also depends what unit evaluation you use again. So for instance, when you looked into, when you use tons as a diversity, as a unit to measure their flows of foods, then we find that in 10 out of 14 cases, import diversity increases. While when we use US dollars, we find that only in 2 cases out of 14 import diversity increases. So it really matters what is your unit evaluation, whether you value in monetary units or in tons or in calories, it seems to be caloric valuation seems to be somewhere in between tons and US dollars. So yeah, a few key takeaways, and I've already discussed some of them, so I'll probably just keep it as on the screen and happy to take questions.
Very much. Okay. Questions, comments?
Then which measure do you recommend? Like tons, calories?
Yeah, that's a good question, and I suppose it also depends, whether it's like you measure more from the economic point of view, so like food security from a food affordability point of view, or it's more supply from the nutrition perspective, like caloric affordability. Probably using calories, I would think would be more appropriate than tons, because it's a more representative measure in terms of your energy intakes. But otherwise, I think there is this just nutritional versus economic kind of perspective. But also, I think it's important to point it out, right? Because then we would have differences. So many, P models would use calories or tons, while G models would use money metric values. So, there is this difference. As the
It might be good to focus as well on some key sensitive. Because, countries like Japan and India are really concerned about one big commodity. So, if I can't import my mangoes from Colombia, so what? I don't really care. But, if rice, is critical to my economy. Yeah. So rather than look at it kind of from the aggregate point of view, just focus on some of the key sensitive.
Yeah. So what we did here, we took into account both sourcing of countries and commodity mix. So it's a sheer commodity times country. We can obviously aggregate across commodities or across countries, right? So which would be other dimensions. We did aggregate across commodities, and results were relatively similar. So when you just use, all aggregate inputs from country, but commodity dimension would be another option to look into.
Alexander, very quickly, my apologies, I think I missed it. How will behave the soybean exports in the case of the US?
So
You show a decrease in terms for Brazil, makes sense, big exporter, but how is going to behave in the case of the US? And I know that it's not disaggregated for other peers such as Argentina.
well, we do have soybean as a separate, oilseeds as a separate sector. As far as I recall, there would be a decline in demand, so exports would decline. Now, whether they would decline more than exports from Brazil, that's something we can check, right? So, and then getting to the Dominic's comment on looking into specific commodity, right?
Yeah.
Well, good. So I think that we've exhausted the time, and we are ready to close the session. Thank you very much for all your help. That was really, really good. Thank you very much. Geraldo, do you want to say some comments about what, as an external person from
All participants.
what have you seen from this session?
I really enjoy it because very interesting progress in terms of database and also in modeling approach. It was really nice to see the updates in database. For example, Maxime, you showed that you have recently updated from FAO. Also, I think that all of you have highlighted that despite the progress, there is still a huge road to go. There are opportunities, a lot to do. Rob's work in terms of, going to the state level, I think this is going to be.
That's really good.
Yeah, it's really good. And we have been discussing a little bit with Dominic last year or a few years ago. That would be great if we could, in the future, put together a grid cell level to the state level, to the national, and then the global level. But again,
at least for the big countries, it would be so good to have this state trade. And this leads a little bit to what you are doing as well.
And we're kind of coming at it from the other way, but we're going county to national. Now we'd like to build in the national piece. Right. So.
We know we can do, the US is well underway. Brazil is doable. China is working on this. Canada is working on it. Australia probably could do it as well. One technical issue is combining this in a single model is a problem because of nomenclature. US has 51 entities, Brazil, I don't know, 27 or 28. So it becomes kind of a modeling problem because you have different sub-regional dimensions.
So, yeah,
Yeah, that's a technical.
Yeah.
but thank you very much. Lots and lots of progress.
Last thought, Mario, is that things are changing very fast. So I think our modeling effort some way need to change our baseline scenario. The baseline is different now. So we need to incorporate that in order to make perhaps to bring better perspectives.
Yeah, and see what's
And it was super nice to see Siwa. Siwa is like you, Mario. I think I haven't seen him like for 15 years.
At least.
No, but see what the same, including aquaculture seems to be a frontier that we really need to
Exactly.
take seriously and incorporate in all the flows, it will give the completeness and consistency, and especially for any work on food, it's actually quite essential. Any comments from the online participants?
Great feedback. Thank you all for your attention, and I wish I could be enjoying a tequila with you in Mexico, but maybe hopefully next time. Or
Absolutely.
caipirinha
Next
with
time.
Geraldo.
Okay, we'll see what.
Yeah, thank you all. Interesting talks, especially about units. I think about that a lot. Yeah.
Thank you. Cool.